Okay, so I'm going to be talking about recitation 4, where we'll discuss Monte Carlo methods, temporal difference methods, Monte Carlo tree search, and some intuition about ImageNet. So Monte Carlo is a method where you update your value function using the average of your returns, and then after you do this, you kind of so essentially how you do this is you collect samples from your environment, so a set of state, action, reward trajectories. Then at the end of the trajectory, you update each of the states that you've encountered with the average return, and return is computed as the sum of the discounted rewards. So essentially this quantity right here. And rather than storing all of the rewards and then doing it that way, you can use this incremental update, which essentially uses the visit count and the previous value function and does an incremental update that way. So the distinction between Monte Carlo and DP is that in Monte Carlo, you do a single trajectory and you update all of the states from within that trajectory, whereas in DP, which includes value and policy iteration, you iterate through all of the states and update all of the states, and this actually requires full knowledge of the environment, so the transition function and the reward function. And an important distinction between the two is that DP has a biased estimate because it uses a one-step bootstrap, whereas Monte Carlo is an average over a bunch of returns and thus is unbiased, but it has a lot higher variance. And an important thing about Monte Carlo learning is that it assumes that all trajectories are episodic, so that means it terminates at some state t. So here's a visualization of the backup diagram of DP versus Monte Carlo. In DP, you can see that it only goes down one layer, and it uses the value function from the next state to compute the value function of the current state. And it does this across all of the future states. On the other hand, Monte Carlo goes down all the way down the tree until the terminal state, and only updates states along this trajectory, and it isn't wide because it doesn't consider multiple different possibilities, only the actions that were taken within that trajectory. So this is the pseudocode for Monte Carlo. So the goal of Monte Carlo prediction is predicting the value function for a certain policy. So you give it as input the policy to be evaluated. You start with the value function initialized arbitrarily. Normally you just initialize it all to zeros, but if you have some better initialization method based on prior knowledge, you can use that instead. Then you initialize the returns as an empty list for each of the states. And you essentially perform a sequence of trajectories within the environment. So for each episode, you follow your policy pi, and you generate the state, action, reward trajectory. You initialize the return to 0, and you aggregate backwards on your return to compute the return starting from state S sub t. So how you compute that is your return for your state t would be the reward at t plus 1 plus your return after state t. So you essentially add all of these returns to their corresponding states, and your value function is computed as the average of all of those returns. Based on like an optimization we saw on the previous slide, rather than holding all the returns in a list, you can simply do the incremental update where you do 1 over n times the difference and use that as your update rule. So if you want to also generate a policy for this based for this problem, how would you do that? Does anybody have any ideas? So think of what sort of additional information you need besides a value function if you want to generate a better policy than the current policy. Yeah.
Action reward expectation.
Yeah, so you would need Q values. So that'll if you have both your state and actions pairs to and compute these same values from them, you can use argmax of your Q function to tell you the optimal action to take, or at least a better action than the current one. Are there any questions on that?
If no one have any question about the Monte Carlo method, I will discuss about temporal difference learning. So Monte Carlo method is unbiased, but it can sometimes have some questions. When it assumes that the trajectory should be terminated, otherwise it will not work because we need to sample the whole trajectory for Monte Carlo method. Also, if the trajectory is very long, when you do Monte Carlo updates, it will take a lot of memory and computational resources. In such cases, Monte Carlo methods will not work very well. And then we will turn to the temporal difference learning. Basically, temporal difference learning is that for the previous slide, we can say that gt equals rt plus 1 and plus gamma rt plus 2 to the end. And we are basically replacing the gamma rt plus 2 to the end with the value function at state t plus 1. And we use the value function to approximate the sum of the future discounted returns. And we can see there is an alpha here, and we can set the alpha to be the fixed value. In practical, if the alpha is very small, it's actually very equivalent to the 1 over n, the number of states st. So in practice, we do this, and I have mentioned that however, replace the discounted return with value function will introduce the bias in the target. And the original version of TD just using the actually using the reward at time step t plus 1 and using the value function to approximate further returns. And however, this one will be very will sometimes be unstable. Then we further develop TD to have n-step returns. Basically, we use the exact return for n steps, and starting from step n plus 1, we using the value function to approximate the future returns. And we can say that the n-step TD learning will have less reliance on the value function. And typically, unlike the original version of TD, the n-step return will be much more stable. And you will probably need to implement the original version of TD and n-step TD in the homework. And you will observe such trends on your own. And this is the diagram for the n-step TD. And we can see that This is just the situation when n equals 2. Next, we will introduce the Q-learning and off-policy TD learning. So for the original slide, we are using the value function. The input is the state. And for Q function, we have the state and action pair. And the key difference is that for when we approximate future returns start from t plus 2, we are taking the maximum value of the Q function. And the key benefit is that it's off policy. So basically, the policy you are used to select the action is different from the policy you update the Q function, and it only requires state action, reward, and next state pairs draw from the Markov decision process. And yeah, as I said before, it doesn't depend on the policy anywhere, and it brings huge sample efficiency, and it is the foundation for almost all sample efficient IL methods. And the issue for reinforcement learning is that when the state space and action space grows too large, and we cannot use the tabular Q-learning, because in order to create such a table, it's almost impossible. Also, some state and action pairs may be visited very less often than some than others, and in this way, we can using a function approximation to approximate the Q values. Basically, the function approximator is a neural network. Then we can use the gradient descent to minimize the Bellman error. So, basically, we have the target value and we have the prediction. We want the prediction to be as close to the target value as possible. So that's why we use the MSE loss, and we can see that there is SG here. The SG denotes stop gradient. For the target value, you must stop gradient because this is just a reference value. If you do not stop gradient, the original TD learning will probably fail because it's very unstable. Also, however, in your homework, you may observe that even if you do not stop gradients, for n-step TD learning, if n is large, it will probably work, but the plot you get will be very different from our solutions. So in the homework, we recommend that you first try the original version of TD and to see if it's working or not. Otherwise, the n-step TD you implement will probably be incorrect. And yeah, so this is the updated rule for function approximation, and we have to stop gradient for this part. This is very essential. Yeah, for the original version of the TD, we have a target network as well. Because one problem is that when you update the Q function, your target will probably change. And if you are chasing a moving target, it's very easy for the function to confuse about which one is the correct target. And this is where most instability comes, and sometimes we may even have unintended generalization to other states, and this will lead to error propagation through the trajectory. The original error may be small. However, if the error propagates after several steps, the error will be huge. And the solution is that we can update the target network every t gradient steps. So basically, for t steps, you are fixing the target network, and after that, you update the target network once and continue update your value function for t steps, and repeat this process. In this way, network will have more time to fit targets, and also it will slow down training, but it will bring you stability. Sometimes without target network, it will probably not work at all. And another trick is that experience replay. As I mentioned before, Q-learning is an off-policy method, which means we can actually collect the state reward action and next state tuple to reuse these all these samples. And also, online samples tend to be very correlated. This can lead to unstable optimization. And when we in machine learning, we often assume that samples are drawn from the distribution IID, independent, identically distributed, and sometimes that's why correlated samples will sometimes cause some trouble. And if we have such a replay buffer and put all our previous experiences into that replay buffer, and we sample from the replay buffer, then the correlation between samples will be much more smaller if we are just using the online samples. Yeah, so basically that's the trick for experience replay. And when you do your homework, you have to decide the hyperparameter for the size of the replay buffer. So if the replay buffer is too small, then you will probably when you do the training, you will probably not be able to find the best Q function because the replay buffer is too small, and the network can forget the how to behave at the initial point. This is due to the catastrophic forgetting. However, if your replay buffer is too large, you will not be able to sample better actions, the better tuples, because the probability of sample such action is small. You also have some very so you also have some less ideal paths in the pairs in the replay buffers. Yeah, so basically that's for the temporal difference learning and the deep Q learning.
Good question. Is T usually fixed, or does it ever change in practice, like during training?
It's a hyperparameter, so you can set it to be fixed.
Is there any benefit to like changing it? Like I know with some hyperparameters like learning rate that changes over time. Is there a benefit to like having a short T in the beginning when your policy is bad, and then lengthening it in the future when it's better?
You will probably need a larger T in the beginning because because when you initialize the network, basically it's random. And if you are using the short T, it can change a lot. And when your policy gets better and better, it will be probably stable, more stable than before. But we often fix that T.
Okay, so now I'll discuss about Monte Carlo tree search. So the problem with the methods that we've seen so far is that it's nearly impossible to estimate value functions at every state if you have a very, very large MDP. So for instance, if you have the game of chess, there's 10 to the 48 states. So that's impossible for any tabular method. And even Monte Carlo and TD methods don't work as well because they rely on the fact that every state and every state action method has been visited. And if you don't have those, you'll essentially have no information about those state and action pairs. And thus you can't make any reasonable predictions. So essentially what you can do is use a neural network or some other technique like in DQNs to sort of measure these, kind of predict what those unknown states would be. Yeah, and this is like a kind of alternative to that. Okay, so Monte Carlo tree search essentially uses a technique called online planning. So that's essentially when you use an internal model of your dynamics to simulate trajectories at your current state in order to find the best action to take. How Monte Carlo tree search works is that it only measures value functions for the important parts of your state space. So states that are visited often, for instance, like the first state, and states near that first state should be measured a lot more frequently than some arbitrary state that doesn't really occur that often. So essentially, this allows you to only keep track of part of the MDP, which gives it a lot more flexibility. So Monte Carlo tree search consists of 4 steps. You have selection, expansion, simulation, and backup. So just some basic terminology. These nodes represent each of the states. These black edges represent actions between those states. And the tree, which is like the tree internal state, only considers a portion of your states and actions. And it stores Q values and for those actions. And of course, just like any other Monte Carlo method, it requires you to be able to go all the way down to episode termination to update your values. So the first step is selection. So essentially, when you your previously known tree, all you can do is follow UCB because you already have information about these states and actions. So you can kind of use this intelligence exploration method to identify which states and actions you should visit more often because they've been proven to do well in the end. Does anybody have questions about selection? Yeah, so this is the pseudocode for it. If all of the children are expanded, then you can use your UCB sample based on that, and then you keep continuing that process until you get to a node where all the children, or not all of the children, are expanded. In that case, you explore this one of those children which have not been explored yet. So that's the expansion phase. So you arrive at some state that you haven't seen before. And after that, you decide whether or not you want to add that state to the tree. Normally, you don't want your tree to get too deep, so you only add it one of those states are limited at a maximum depth. And then after that, you get to the simulation phase. So when you're at that new action, a new state, you kind of don't know anything about your environment. And so you really only have one choice, and that's to like keep exploring until the end. And normally you use a rollout policy, which is random and just go down all the way. And you arrive at a terminal state and you receive your reward. And finally, with that reward, you can back up all the way and update your previous Q values. So note that you only want to update the values that are already in your tree. You don't add the simulated states to your tree. So you just, for each of your Q values, you compute the return up after that Q value, and then you update using the incremental update rule from before. Does anybody have any questions about how MCTS works? Okay, so overall for MCTS, you just keep repeating these 4 steps again and again until like some time limit, or if you notice that your Q values are converging on specific at specific values for each of your states, then that means that your state value function has been essentially optimal. And then using these Q values, you can essentially identify the best action and essentially just do the argmax and go down all the way down the tree. And so one optimization you can do to MCTS is for each state, rather than simply recreating the tree after performing a single action, you reuse that subpart of the tree after executing that action in the real environment. And so you don't have to regenerate that tree from scratch. Does this make sense? Okay, so there's a few scenarios where MCTS works a lot better than the previous methods that we talked about. If you have a limited amount of time, that's more useful because you only explore a small part of your state space. For MCTS, you do need an internal model of the dynamics because your simulation phase occurs within the environment, and you need to know the transitions and rewards to do this. And yeah, so it doesn't matter how big the state action space is, because Monte Carlo tree search focuses its exploration on only the best options based on UCB. Okay, does anybody have any questions about MCTS? Okay, so now I'll talk about the ImageNet dataset. This is a dataset for visual object recognition. It consists of millions of images and tens of thousands of categories, and it essentially provides a sort of like classification task for images, and it has a hierarchy of different categories that it uses. For instance, it goes like all the way from like general terms like mammal and vehicle down to like specific breeds of dogs and specific types of sailboats. So the primary task that you do with ImageNet is predict bounding boxes and identify the like the image within the bounding box. So here you're identifying this box and this box are like 2 kit foxes. So yeah, there's about 150 images per class, and there's over 3,000 classes. So that's like a very, very complex problem. It's been kind of the most common benchmark data set for image classification. And so when AlexNet was released in 2012 and improved the accuracy or the error rate from 25% to 15%, it really put deep learning on the map because it's like a huge improvement to go essentially 10% improvement in error rate. And that kind of started the deep learning revolution. So AlexNet is a CNN architecture that works as shown in the diagram. Essentially, there's one GPU. There's two GPUs, and the first GPU runs like one set of convolutions independently from the second part, which runs another set of convolutions, and then the result of the two are combined together. And this performed very well in the 2012 ImageNet competition. In 2015, there were major improvements to this. You essentially add residual connections. So that means you add from one layer, you add its input to the output of that layer. And thus you can allow for easier gradient propagation. And note in this case, the top 5 error ended up being 3%, which is a huge improvement. So in the modern age, there's been a lot more improvements. The top 5 errors down to like less than 1% now. And even like the top 1 error is down to like 10%, as opposed to AlexNet where it was like over 40%. So there's been huge gains made over the past few years, and these transfer directly into reinforcement learning problems because the kind of goal of reinforcement learning is usually to explore a very large state space, and that state space tends to be visual in nature. So these sort of advancements are very useful in that case. That's it for recitation 4.